Now is the do now, and we're going over to look at the first student's paper that has it. And what we see is a definition probably off the internet. Yeah, okay. And it says the strong acid means that in aqueous solution at standard temperature and pressure. See, there's a lot of stuff that we don't talk about that's really part of it, and that actually belongs there. But I certainly wouldn't take anything off for not having it. But the concentration of hydronium ions is equal to the concentration of the strong acid itself. Let's take a look and see what that means, because I don't think Clyde could tell us. All right? Yeah. Okay. And that's all right. But at equilibrium, that means, oh, we can't do that. We got to go back here and release the screen. And now it should go. Yeah? Okay. No, it doesn't go. Unfreeze, please. There we go. Okay, dissociate is what happens, by the way, when molecules ionize. Dissociation and ionization are essentially the same thing. I'd like you to get that into your notes. Acid ions. The concentration of acid ions. Let's look at a strong acid, HCl. Notice the arrow's one way. What does that mean? It ionizes how much? All the way, or 100%. Okay? So this is going to form hydrogen ions, and it's going to form chloride ions. And when we get going on the lesson, you're going to find out that hydrogen ions really aren't going to be around for more than a nanosecond, because they're going to bump into water molecules and become hydronium ions, H3O. At any rate, if we start with 100 of these, what that definition that Clyde had, what that meant was this is going to go to 0, and this is going to go to 100. And when this goes to 100, then that means that the chloride will also have to go to 100. So we start out over here. It was 100. That goes to 0. That means it's going to dissociate 100%, which means that every single one of those is going to become one of these and one of these. Dissociation, also called ionization. Same thing. Okay? According to David's definition of metal, David, can you give us a metal? Copper. Okay. Copper, let's say it's copper 2. So there'd be 2 hydroxides. Okay? So copper can be either a +1 or a +2. If he's a +2, he'll have 2 hydroxides. And this guy is going to the other side of the equation. Again, he will be a strong base. So there's going to be copper 2 ions. And there's going to be 2 hydroxide ions. That's going to be a good strong base. The first hydroxide is going to come off very easily. The second one, not so easy. But certainly the copper as +2, or yeah, the +2 copper that we see over here will have 2 hydroxide ions. And so at least one of these guys is going to get into the water, because that's going to be a strong base. The guy that happens next, if we have copper with OH as a 1- going to copper 2 plus 1 hydroxide, and really we should have done the first ionization this way. There, one of those, and one of those hydroxides and one of the coppers. And then here we would have 1 copper and 1 hydroxide. This guy is going to want to go probably more this way, just like we do with acids. Remember the first ionization of an acid? Yeah. Okay, the first guy coming off, very easy. Second guy, a little harder. Third guy, like pulling teeth. Okay. It's not going to come off very easily. So there's your strong and weak acids. From yesterday, you can see the pictures up above. These guys are pictures right out of the textbook, and you might remember that the bright guy on the left was with the strong acid, and this guy I did with ammonium, which is a weak base, and it just doesn't do much.
But if you plug it in and then you put the acid in, right, it goes right. But if you don't put acid and you just touch the metal, will it shock you? Since it's passing electric current.
What? That's just a brief reminder of yesterday. Now let's go down to what I wanted to show you for today. Let's see if we can get these guys straight and really understand what's going on. Well, I'm going to pick someone. Look over at the left-hand circle. Now, this graphic is taken right out of page 603 in your textbook, so you can go back and look at that at home. The only thing that's not on your graphic in the textbook is this stuff right here, in blue. I put the whole formula or the equation for the strong acid, the HCl, and that guy's on the left. And then I put this guy as a weak acid because acetic acid is a weak acid. And if this is a weak acid, should I have any other arrow in there? Anyone? It's a weak acid. Should I have another arrow? Well, it's a yes. And the reason it's a yes is because that arrow is going like that.
Oh, yeah.
Probably about 10 times that long. Okay? Because this guy does not want to ionize much. And we'll see some ionization stuff in just a moment where you can see actual numbers for these. And you'll know how small these ionization things are. So Lizzie, let's take a look over here on the left-hand side. Okay, now we can concentrate. Would you look on the left-hand one and notice that right here I've drawn a green circle? That's the chloride ion. Okay? And here they actually show the charge, but they don't show the charge on all the rest. Okay? Just get you oriented. And this guy is what happens to these hydrogens when they get into the water. Okay? They're not going to stick around as hydrogen ions for more than a nanosecond. That's not very long. Nanosecond. That's 1 over 1 with 8 zeros. 9 zeros, sorry. That's a billion. 1 out of a billion. So, let's go ahead and look now at this guy. He's the hydronium ion. And like this hydronium doesn't have plus charges, or the other hydroniums will not have plus charges. See, this guy doesn't have a plus charge, nor does this one. So what I'd like you to do is give me a count of the chlorines and the hydronium ions. How many of each? Okay, so there are 12 hydronium ions, and how many chloride ions? 12. So we got 12 and 12. Now, if we have 12 and 12, what does that mean about hydrochloric acid? Is it a strong or a weak? Listen, please. Think for yourself, listen. Don't listen to it. It is strong. Good. Okay, so this guy dissociates 100%, and that's what it looks like when it's 100% dissociated. If it were together, it would be this guy, and you'd be seeing the whole molecule as it existed on the left side. But there aren't any of those. That means it dissociated 100%. Okay? So let's go over to the other dude now and focus on him. There we go. This one goes to Edward. Okay? Edward, let me get you oriented a little bit. This guy is this thing here, the acetic acid. Okay? And you'll see him here, here, here. In fact, you'll see him everywhere except here. Because what's hard to see in this graphic is where that hydrogen is that gets lost. The hydrogen that will come loose is the one that's on the oxygen, one of the oxygen atoms. Now you can see it on the back here. It's not very visible, but it's there. You can see it here. You can see it here really well because the molecule is turned toward us. But each of these guys, except this one, has one of those hydrogens on it, which means that this is the only acetate in the water. Okay? This is one hydronium ion, and that's the only one in the whole group. So how many total acetic acid molecules do we have? We have 9 acetic acid molecules, okay? And we have one of these and one of these. So what happened here? We started out up here, we had 10. Here, let's do green. We had 10 of these guys. One of them dissociated. Now we have 9. How many hydrogens should we have?
Actually,
The hydrogens in the middle of this molecule, these guys don't go anywhere. This is the only one that leaves, because this is part of the acetate ion. Okay? So, if we dissociate 1, see we started with 10, now we have 9, how many of these will we have? Huh? Why are you going to have 2? There's only one of them in a molecule. These guys don't go anywhere. Okay, so how many of these do we have? Just the H. Okay, it's just one. Okay, so we got one of these, and because we're dissociating this guy, which means we're taking the hydrogen off the acetate ion. The acetate ion is left by itself. So we have one of these and one of these because one of these will make 1 and 1 when we take it apart. Are we good?
yes.
Okay. So, is this a strong or a weak acid? It's weak because it only dissociates a little bit. In fact, it dissociates a whole lot more, or a whole lot less than this picture would indicate. It's more like, well, let's look at the actual numbers. Here we go. Do we have acetic acid in this thing here? Yeah, we do. 10 to the minus 5. That means if you have 10,000 molecules, 1 will dissociate.
All of them are weak acids, correct?
These are really weak acids, yes. All of them. And what's the weakest acid in the whole group?
Natrium.
Okay? The biggest negative number. That's essentially nothing. You know, 1 with 9 zeros on the bottom of the fraction, top of the fraction is the number 1. It's not very much, right? So really, really, really small. So this is an exceptionally weak acid, but this guy's not so bad. It gives you some. 8 zeros, that means you have 10,000 molecules, and one of them dissociates. Yes. I know it's 10 to the minus 19. Oh, if you did, if I said that, I didn't mean it. It's 19. Yeah. Okay, so this guy a lot stronger than this. As we saw with other things when we were doing dissociation, pulling the first hydrogen off is easier, like the sulfuric acid. It's 100%. Pulling the second one off, that's harder. And you can see that with, let's see. Do we have any other multiple hydrogens? No, just that one. But you can see the weak acids, the concentrations are really small. Okay, so you just don't get too much. All right, let's go back here and let's talk about this guy. Have we done this? Yeah, let's go back to here. How are the ionization equations for strong acids different than the weak acids? That question goes to Hike. Okay, take a look at them, Hike. Tell us what you think. Okay, here's all your strong acids, and all your weak acids are down here. In what way are they different? Let him find it on his own. Okay, so what we finally realized is that there's double arrows here on all the weak acids, and single arrows on the right, going to the right only, which means we're getting 100% dissociation. Now, especially with this guy, yeah, we're getting 100% dissociation, but that's only on the first hydrogen. Okay? The other hydrogen is going to be pretty tight there. It's going to be more like 10 to the minus 9 or 10. Okay, it's going to be a huge, or a very, very small number with a large minus exponent. Okay? On the second one. To get rid of this hydrogen, that's going to be tough. So what I'm asking you to do right now, if you're listening at home, is stop the recording after we answer these couple of questions. And then you're going to do the same assignment that I'm asking people to do in class to help make sure that you understand case of equilibrium. So let's go to William. You're on. How are the ionization equations for strong acids different from the ionization of weak acids? We just said that. Remember what that was?
The weak acids, they go both ways.
Good. Weak acids go both ways. All right, now let's go down here. What do the double arrows indicate? They're backwards, forwards. The backward-forward motion is the same after we get to what? Starts with an E. Yes, good. Okay, so at equilibrium, the forward and the reverse reactions become exactly the same. The rate of them. Okay, let's imagine you're in a car and you're about to come to a bridge. The bridge is about a couple of miles long. Okay? It's a big bridge, like the Oakland Bay Bridge. Okay? I think it's only a mile, maybe a little less, but it's a long bridge. Okay, so you start over on that bridge. You're at the head of 100 cars. Okay? And there's 100 cars on the other side of the bridge. Fortunately, they are also on the other side of the road. Okay? Now, I'm going to start both sides at the same time, and both sides are going to go the same speed. When everybody's across the bridge, the side that you're on is across, and the side that was the other side, their 100, has gotten across. Have we changed the number of cars on each side of the bridge? Okay. And indeed what happens is we keep having 100 cars go, say, every 10 minutes. One way and the other. Now in the morning, the traffic is heavier one direction. Right? Than it is in the other direction. And then the equilibrium is going to change. Right? Yeah. Okay. So that's the way that kind of thing works. So you're absolutely right. You understand what those double arrows mean? It means that it has become an equilibrium reaction. And what I'd like all of you to do right now is write a K sub EQ for the guys that I have circled here. And I'll make these bigger so that you can see them. So, be sure that you remember who goes on the top side of the K sub equilibrium and who goes on the bottom. And after we stand, I'll be able to talk to you about something called K sub A.
Write down the equation of the QA.
Okay, we want to put these guys in, right? Because these are ions. Okay, and this is HF down here, and that should be in brackets. Yeah? Okay. Now, you don't want to do this either. You want to I'm going to put your full bracket there. Were you in kind of a hurry? Yeah. Okay, here we go. Let's go back and let's look at the next one. We're going to be doing this guy, and my lucky is Sose. Okay, would you bring your paper up, please? And let's see how you did. For acetic acid ionization, this would be our K sub EQ, and as you're going to see in just a minute, these guys are going to become a K sub A. Or, what do you think the A stands for, folks?
Aqueous.
Aqueous. Very good, Kenneth. Okay, so here's the equation, and you should have copied these down, as well as the K sub EQ. All right, the next one will be for, thank you. The next one will be for carbonic acid. Matt has written down the equation, and the equation becomes the K sub EQ, or K sub A, because this is an acid. And the K sub A is really just K sub EQ, but it's specific to an acid. What will it be for bases? K sub B, sure. What do you think it'll be for water? K sub W. Yeah, very good. Okay, so this guy, hydrogen ion, the HCO3 ion, and then we've got this is actually called a bicarbonate ion, and this dude right here is the carbonic acid. And all in brackets, you even got the charges, looking very good. Thank you. Now, for this question, why is it that B is correct? And the question goes to David Saturian. Why is B correct? Yeah, but why do we know that that's not a double, why do we know that that is a strong acid instead of a weak acid? What tells you? What's the dead giveaway? One arrow. Good. All right. Excellent. Okay, we're going to change the question. Oh. So now we're asking you, when you look at this equation, would you say this is a blank base, A, B, C, or D? So the majority do have the correct answer here, and Alexa's not here, so Alfredo, why is B the correct answer for this particular equation? It only has one arrow. Very good. The arrow is only pointing one direction. Okay, new question. Okay, you're looking at H2S, that's hydrosulfuric acid, and then you want to answer A, B, C, or D, and of course this is an acid. What is it and why? Folks, if you're not getting these right, you really need to figure out what's going on. Okay, 1, 2, 3. Okay, you made it. All right, D is the correct answer, and we need to know why. Daniel? How do you know it's weak? Were you listening to the other two?
I didn't get it right.
Yeah, I understand that. Were you listening to the other two answers? Yes, of course it's D. I told you that. Very good. Just that simple. Okay, you're smart enough to figure that out, man. You're just not paying attention. Okay, let's put the responders away. We got one little part of this lesson left. Okay, we're done. Okay, good. Here we go, the last little part of the lesson. This K sub EQ is a K sub EQ for this reaction here. If we take it down here and have that equal to the K sub EQ of water, that's actually K sub W. But we're going to do the K sub A, or the acid equilibrium, for the dissociation of HCN, which is hydrocyanic acid. Now, yeah, it would be good if it were in your notes, because this is important stuff. This is probably the most important part of what we did today, or what we're doing today. Look at that constant, how low that is. Does that mean that the top is smaller than the bottom? If the top is smaller than the bottom, it would have to be a negative exponent, because it's going to be less than 1, right? Because there's more HCN than there is this stuff, meaning that, okay, this K sub A, called the acid ionization constant. So, because that's small, that K sub A has got to be less than 1, and 10 to the minus 10, that's a really, really small amount of product. So the ionization of a weak acid is what we were seeing right here. The value of K sub E indicates the reactants or products are favored at equilibrium. If it's going to be a number bigger than 1, that means the reactants are favored. If it's a number smaller than 1, that means the products are favored. I think I said that backwards, so I'm going to repeat. Okay, if K sub A indicates whether the reactants or products are favored at equilibrium, this means that the reactants are favored because we have a power of 10 that's negative, which is really, really, really small, which means that we don't get much of these. If this were 6.2 times nothing, or 1 times nothing actually, this guy is going to essentially get smaller and smaller, and it could get up to a power of 10 to the 1. I mean, we're talking about this guy really getting small or disappearing altogether. And when I say 10 to the positive 10, we are really getting everything into the products. So a number bigger than 1 favors the products, I'm saying it right this time, and a number smaller than 1 means that the big guy is on the bottom, which means we don't have much of these being formed, which is the situation with this particular K sub A. So, concentrations of ions, products, in the numerator tend to be small compared to the concentration of unionized molecules in the denominator. And that's for the weak acids and weak bases as well. The weakest acids now have the smallest K sub A. Okay, 10 to the minus 10 is pretty small. And the lowest concentration of ions, which we would consider products, have the highest concentrations of unionized molecules. So, there we have it. And I hope that you found this helpful. That's the end of our lesson.